students. So, the earlier classes we already discussed about the 50 unit. We rewind the 50 unit also. Now we will start rewinding the 4th unit, that is a correlation and sampling theorem, right? Correlation and sampling theorem. So here the topics involved in this correlation and sampling theorem are autocorrelation, cross correlation functions, properties of correlation function, energy density spectrum, Parseval's theorem, power density spectrum, relation between convolution and correlation, next detection of periodic signals in the presence of noise by correlation, extraction of signal from noise by filtering, that is related to correlation. And then coming to the sampling theorem, graphical and analytical proof for band limited signals, impulse sampling, natural and flat curve sampling, reconstruction of signal from its samples, effect of undersampling, aliasing, introduction to band pass sampling, and some related problems. These are the topics involved in this correlation and sampling theorem, right? What is meant by correlation? Correlation means nothing but comparison. We will compare two signals, similarity of two signals. So the signals will be compared on the basis of similarity of waveforms. This comparison may be based upon amount of the component of one waveform contained in the other waveform. So let us take two waveforms, x1 of t and x2 of t. These two are arbitrary waveforms. The waveform x1 of t contains an amount of h2 of t of waveform x2 of t in the interval t1 to t2. So it is nothing but x1 of t contains an amount of x2 of t of waveform x2 of t. Okay, so there is a similarity between these two in the interval t1 to t2, where c12 is equal to integral t1 to t2 x1 of t into x2 of t dt by integral t1 to t2 x2 square t. This is nothing but equation number 1. If the numerator is 0, then c12 becomes 0. So then these two signals are said to be orthogonal signals, as which two are mutually perpendicular to each other. So integral t1 to t2 x1 of t x2 of t dt is equal to 0. So comparison is completely depends on the numerator of equation number 1, right? In general, we are interested in comparing the two signals over the entire interval, that is beyond the limited interval, that is minus infinity to plus infinity. Then the numerator becomes integral minus infinity to plus infinity x1 of t x2 of t dt. That is equation number 1. Let us take x1 of t. X1 of t is like this. This is x1 of t and this is x2 of t. There is some delay t period is in between x1 of t and x2 of t. These are the two signals. So the above two signals are identical, except that x2 of t is delayed by t seconds with respect to x1 of t. Okay. If we compare these two signals over the entire interval, that is minus infinity to plus infinity, is 0. Okay. So hence, in order to search the similarity between the two signals, we must shift one waveform with respect to the other by various amounts. So test integral is modified as j1 of tau is equal to integral minus infinity to infinity x1 of t into x2 of t minus tau t tau. That is equation number 3, where tau is a searching parameter. So equation number 3 is known as a cross correlation. We are comparing two different signals here, or two different waveforms here, x1 of t and x2 of t. So that's why it is called cross correlation. We are comparing two different signals, right? Okay. So J12 of tau is represents the cross correlation. So cross correlation provides the measure of similarity between two different signals. We have to note that if we shift the function x1 of t by an amount of tau in the negative direction, or shift x2 of t by the same amount in the positive direction, thus it can become J12 of tau equal to integral minus infinity to infinity x1 of t plus tau into x2 of t dt. Let it be taken as equation number 4. So by the above two definitions, this cross correlation can be defined as j12 of tau equal to integral minus infinity to infinity x1 of t into x2 of t minus tau dt, or x1 of t plus tau into x2 of t dt. That is equation number 5. Similarly, j21 of tau equal to integral minus infinity to infinity x2 of t into x1 of t minus tau dt, or x2 of t plus tau into x1 of t dt. That is equation number 6. And from these two equations 5 and 6, J12 of tau is equal to J21 of minus tau. This is the relation between J12 of tau. Both are cross correlated functions. J12 of tau and J21 of tau are related like this. So J12 of tau is equal to J21 of minus tau. That is equation number 7. So that is cross correlation. We are comparing two different signals. That is cross correlation. Suppose a signal is compared with itself only, then it is called autocorrelation. Then it is called autocorrelation. So autocorrelation is defined as this is nothing but the comparison of signal with itself when shifted by an amount of tau. So autocorrelation of signal x1 of t is denoted by J11 of tau. So J11 of tau is equal to integral minus infinity to infinity x1 of t to x1 of t minus 2 dt. Or we can define this as integral minus infinity to infinity x1 of t plus tau into x1 of t dt. That is equation number 8. Then J11 of tau equal to J11 of minus tau. That is equation number 9. Autocorrelation function is an even function of tau. Hence J11 of tau equal to J11 of minus tau. Okay. Next we will see the relation between correlation and convolution. Correlation and convolution, how these two are related. So convolution, suppose if we take the convolution of two signals x1 of t and x2 of t is defined as rho 1 2 is equal to x1 of t convoluted with x2 of t, right? Rho 1 2 equal to x1 of t convoluted with x2 of t. This is defined as integral minus infinity to infinity x1 of t into x2 of t minus tau d tau, right? But for rho 1 2 is equal to x1 of t converted to x2 of minus t, then it is the integral minus infinity infinity x1 of x2 of tau minus t d tau. This is equation number 1, where tau is a dummy variable. Suppose dummy variable may be replaced by another variable k, then tau is replaced by k. So rho 1 2 of t is equal to integral minus infinity infinity x1 of k into x2 of k minus t dk. Changing variables from t to tau, we get rho 1 2 of tau is equal to integral minus infinity infinity x1 of k into x2 of k minus tau dk. That is nothing but rho 1 2 of tau. Rho 1 2 of tau. So rho 1 2 of where rho 1 2 of tau is nothing but integral minus infinity infinity x1 of k into x2 of k minus tau dk. Okay. So hence J1 of tau is equal to x1 of t converted to x2 of minus t. If t equal to tau, then J1 of tau is equal to rho 1 of tau. Similarly, rho 2 J21 of tau is equal to x1 of minus t converted with x2 of t at t equal to tau. That is equal to rho 21 of tau. So therefore, and J11 of tau is equal to x1 of t converted with x1 of minus t at t equal to tau. That is equal to rho 11 of tau. We can say that all the techniques used to evaluate the convolution of two functions can be directly applied to find the correlation of two functions. And one of the function is an even function of t. The cross correlation and the convolution are equivalent. So one of the function is an even function of t, then cross correlation and the convolution both are equivalent. If x2 of t is an even function of t, then x2 of t equal to x2 of minus t, right? x2 of minus t. Autocorrelation of signal x1 of t equal to J11 of tau is equal to x1 of t convoluted with x1 of minus t. If x1 of t is an even signal, then x1 of t is equal to x1 of minus t, that is nothing but x1 of t. So we can say that J11 of tau is equal to x1 of t converted with x1 of t only. That is the equation number 2. Equation number 2 represents an autocorrelation, hence proved. Okay. Next we'll see the properties of correlation functions. Since the convolution of two functions in the time domain is equivalent to the simple multiplication of their transforms in frequency domain. So convolution in time domain will become simple multiplication in frequency domain. Okay, convolution in time domain will become simple multiplication in frequency domain, right? consider x1 of the is an arbitrary signal, right? So suppose if you take the Fourier transform of x of t is x of omega, then Fourier transform of x of minus t is x of minus omega. X of omega is nothing but integral minus infinity to infinity x of t e power minus j omega t. This is nothing but Fourier transform of x of t. Similarly, Fourier transform of x of minus t, that is x of minus omega, is equal to integral minus infinity to infinity x of minus t into e power minus j omega t dt, right? If Fourier transform of x1 of t is x1 of omega and Fourier transform of x2 of t is x2 of omega, then Fourier transform of x1 of t is x1 of minus omega, and Fourier transform of x2 of minus t is x2 of minus omega, and the correlation function j12 of tau is equal to x1 of converted with x2 of minus t, which is nothing but its transformation x1 of omega multiplied by x2 of minus omega. That is equation number 1. And j21 of tau is equal to x2 of t converted with x2 of minus t. In frequency domain, it will become x2 of omega multiplied by x1 of minus omega. That is equation number 2. And j11 of tau is equal to x1 of t converted with x1 of minus t. In frequency domain, it will become x1 of omega into x1 of minus omega. So x1 of t equal to x1 of minus t, that is it is an even function, so it is equal to x1 of t, so it will become mod x1 of omega whole square. So but mod x1 of omega whole square is equal to 5 times of energy of signal x1 of t, because E of x1 is nothing but energy of signal x1 of t. It is defined as 1 by 2 pi integral minus infinity to infinity mod x1 of omega square d omega, right? So that's why therefore mod x1 of omega square is equal to 5 times of e power e of x1. So mod x of omega square is equal to x of omega into x of minus omega. That is equation number 4. Using the equation number 4, equations 2 and 3 may also be expressed as using Fourier transform. Equation number 2 and 3 are x1 of omega is x2 of minus omega is equal to integral minus infinity infinity j12 of tau into e power minus j omega tau d tau. Similarly, x1 of minus omega into x2 of omega is equal to integral minus infinity to infinity j21 of tau into e power minus j omega tau d tau. So mod x1 of omega square is equal to x1 of omega into x1 of minus omega. That is integral minus infinity to infinity j11 of tau into e power minus j omega tau d omega. That is equation number 7. It follows that the Fourier transform of j11 of t is 5 times the energy density function of x1 of t. That is Fourier transform of j11 of t. So therefore, Fourier transform of j11 of t is equal to integral minus infinity infinity j11 of tau into e power minus j omega tau d tau. That is nothing but mod x1 of omega square. Our Fourier transform j11 of t is equal to 5 times of the energy of x1, e of x1. So that is the relation between energy function and the Fourier transform or correlation function. Okay, so Fourier transform j11 of t is equal to 5 times of e of x1. So that is the relation between correlation and convolution. Next, we will see the energy density spectrum. Energy density spectrum. Suppose if you take any electrical system, a signal may represent either voltage or current, right? So consider a voltage V of t is developed across a resistor or producing a current I of t. The instantaneous power dissipated in this resistor is defined by P of t, or P of t equal to V of t into I of t. Or we can write this as V equal to IR, or I equal to V by R. So we replace I of t by V of t by R, then it will become V square t by R. Or if we replace V of t by I of t into R, then it will become I square t into R. In both cases, power P of t is proportional to the square amplitude of the signal, either voltage square or current square. Let me take this P of t. P of t either voltage the x square t is V square of t or I square of t as x square of t. So x of t may be either voltage or current. If R equal to 1, then P of t equal to x square of t, right? X of t may be either voltage or current, right? So non-periodic signals are called energy signals, as we know that Non-periodic signals are energy signals. So energy is calculated for non-periodic signals. So total energy of the continuous time signal x of t is defined by E. So therefore E equal to limit t tends to infinity integral minus t by 2 plus t by 2 x square t dt. Now we can write this as integral minus infinity to infinity x square of t dt. Similarly, for discrete time signals, x of n is defined as E equal to sigma n equal to minus infinity to infinity x square n. Okay, x square n. So x of t, Fourier transform of x of t is x of omega. Then inverse Fourier transform of x of omega is nothing but 1 by 2 pi into integral minus infinity to infinity x of omega. X of omega e power j omega t d omega. That is equation number 1. Energy E of x of t is given by E equal to integral minus infinity infinity x square t dt. Or we can write this as integral minus infinity to infinity x of t into x of t dt. But x of t is nothing but equation number 1. Replace this one of the x of t by this equation, so that it will become substituting the value of x of t as equation number 1. Equation number 2 will become t equal to integral minus infinity to infinity x of t into 1 by 2 by integral minus infinity to infinity x of omega into e power j omega t d omega t dt. Here two integrals are there. So interchanging the order of integration, it will become integral minus infinity to infinity x of omega integral minus infinity to infinity x of t into e power j omega t dt into d omega, right? But it x of t into e power j omega t is nothing but x of minus omega, right? This is x of minus omega. Already x of omega is there, so it is 1 by 2 pi into x of omega into x of minus omega d omega, or it is 1 by 2 pi into integral minus infinity to infinity mod x of omega square into d omega. But omega equal to 2 pi and energy will be defined as integral minus infinity to infinity x square t dt. It is equal to 1 by 2 pi integral minus infinity to infinity x of omega square into d omega, that is 2 pi f. Omega is 2 pi f, so 2 pi 2 pi gets cancelled, so it will become integral minus infinity into mod x of omega square into df. Okay, so for energy density spectrum E equal to integral minus infinity to infinity mod x of omega square into df. This equation states that the energy of the given signal by the area under the mod x of omega square curve integrated with respect to frequency. Okay, respect to frequency. That is about the energy density spectrum. Energy density spectrum. Okay, so these are all the topics we discussed in the today's class. So what is correlation? What is cross correlation? What is the autocorrelation? What is the relation between correlation and convolution? Okay, next energy density spectrum. Okay, so after here we discuss in the today's class. So from tomorrow onwards we will discuss about the interpretation of the energy density and the power density spectrum of the Parsel's theorem for energies, and signals, relation between autocorrelation and energy density spectrum. Okay, and properties of correlation. Okay, all with these topics we will discuss in the next classes. Okay, right? So this